All right. So we've got a nice way of being able to work systems of equations, and especially the ones that are the 3 equations, 3 variables, or certainly anything bigger than that. And the way that we are going to do those is to work with what we call a matrix. Now, officially speaking, the technical definition for a matrix is that we have any sort of rectangular array of information. Now, we're going to want to take that idea and somehow match it up with the systems here eventually, but let's get some basics about these matrices down before we do that. So, generically speaking, we can try to kind of map out a little bit of what's going on to try to help us refer to some of the things that we're going to need later. Because we've got a rectangular array, we need a reference to the row and the column. The row is going to be the first number. The column is going to be the second. So what I'm pointing at here is the entry in row 1, column 1. The entry that I'm pointing at right here is the entry in row M, column 3. And so generically speaking, row M, column N, or I could say just any old entry somewhere in my matrix, row I, column J. So, how big is that matrix? Well, it has M rows, it has N columns, so might as well just go ahead and list it sort of in that way. Rectangles, or say area of a rectangle, length times width, and so we could say the size of a matrix would be like rows by columns. So now it sounds like wood. 2 by 4. Yeah, 2 by 4, 2 rows, 4 columns. But we can say that that's the order or the size of that matrix, and so it does sound a lot like wood. Say a 1 by 1, 1 row, 1 column. 3 by 3, 3 rows, 3 columns. A 3 by 4, 3 rows, 4 columns. Square matrix, not surprisingly, same number of rows as columns. And in that case, we can talk about a diagonal that runs from the upper left corner to the lower right corner. And that particular diagonal having 1s and everything else having 0s is a very special matrix. We call it the identity matrix. It's very special, but for right now, we're not going to use that. We're going to come back to that idea later, which means that I'm going to kind of gloss right over that and move on to a couple of other things that show up a little bit earlier on in our discussion. A row matrix literally has only 1 row, while a column matrix literally only has 1 column. No sort of requirements about whatever else is going on there. But that gives us just some basic terminology and some references to matrices that will allow us to really get into part of the meat of what we want. There's a direct way of being able to deal with systems by using matrices, and then there are some very clever and sophisticated ways of being able to deal with systems using matrices. We're going to start here in this video with just the most direct way, basically using a matrix version that directly corresponds to the steps that the algebraic steps that we saw for solving the systems, where we can, adjust equations and we can add stuff together, et cetera, et cetera. Again, I'm getting there, kind of getting ahead of myself. If we want to transform a system into a matrix, then what we're going to use are all the coefficients. We're going to want to use them in order, so we're back to alphabetical. X, Y, Z, first column, second column, third column. The constants we're going to have over on the right side of the equation. Those are going to be the 4th column. If we needed to have 4 variables, that would be in first variable, second variable, third variable, 4th variable, and then our constants for a column number 5. The number of equations that we have is going to control the number of rows. So first equation in the first row, second equation in the second row, third equation in the third row. You can see that I'm color coding those to kind of help demonstrate that. And so that augmented matrix is what we call that. That augmented matrix directly corresponds to our system. Put a little line in there that separates the coefficients from the constants. Not everybody does that, and certainly we're not going to be able to put that into our calculator when we enter matrices. However, we are going to be able to enter matrices into our calculator and kind of help ourselves along the way. Referring to just the coefficients, notice that this is a square matrix. It only contains the coefficients of the x, y, and z value, the x, y, and z variables in our system. So we might end up coming back to this as well, but for right now, what can we do in the most basic sense with these matrices that help us with systems? So we have what we refer to as elementary row operations. We can switch out rows. And again, because this corresponds to systems, that goes to the idea that we can change the order that those equations show up without changing the system. So if I take the first equation and move it to the third equation, big whoop. It doesn't change the system itself, it just changes the order that those equations appear, which, again, big whoop. We can multiply a row by a non-zero constant, a non-zero number. We can't completely wipe out an equation. Oh, I'm going to multiply by 0. No, you can't do that. You're supposed to have that equation as part of your system. You can't just decide you're going to nuke the thing out of existence. But we saw with equations that if we needed to, we could say, I can take equation 2, I can multiply it by a -3. Okay. Well, if we can do that with an equation, then we should be able to do that with a row, because the row represents an equation. And with the idea of what we've seen we can do with the equations, not only are we able to multiply equations by numbers, but we're able to add equations together, sometimes without multiplying first, sometimes with multiplying first. So the third kind of elementary row operation we have is we can take a multiple of one row, add it to another row, and whether or not we multiply each one first or not. Now, one of the rows is preserved and the other row is replaced, and this is again is following the same sort of ideas that we had with manipulating our equations. We would create a new equation. We would still have to keep the one of the old ones that we had used. We get a new one that comes out of it that should hopefully be a little nicer and friendlier for us to work with. And so that's the idea. By making these kinds of row operations, what we create are called row equivalent matrices. Basically what we want to do, kind of like we did with systems, instead of working with equations and trying to get nicer, friendlier, prettier looking equations, we're working with matrices. So we want to use row operations and we want to try to transform a matrix into a nice, new, prettier looking matrix. Pretty how? Oh, good question. Pretty in two possible ways. The first way that we can come up with a somewhat prettier matrix is by creating what we call row echelon form. Any row of zeros that we've got gets shuffled to the bottom. That just kind of takes care of the extra padding that might happen with certain kinds of problems. More importantly, every row that we have other than a row of zeros is going to start with a 1. The leading ones that we've got as we move from row to row are going to move over to the right. So it kind of goes like this. Leading 1, leading 1, leading 1. They got to create a bit of this slant, which means that underneath of these leading ones, we're seeing zeros. Only above the leading ones are we seeing other entries. but all of those rows are starting with 1s except for anything at the bottom, which is all fluff. It's all rows of zeros if that is something that shows up. So that's what these are saying to us. Now let's try to demonstrate that a little bit so that things are a little bit nicer to us. So first of all, some examples here about what we can accomplish. First of all, taking that system from before, we had the augmented matrix. We can say that we can interchange two rows. So just for kicks, we're going to switch out row 2 and row 3. Row 1 stays the same. Row 3 is now sitting in row 2. Row 2 is now sitting in row 3. Clearly that didn't do very much for me, but again, I can do that. That's allowed. Multiply a row by a non-zero constant. So just for kicks, we're going to take -1 times row 3. Okay, that means every entry in that row got multiplied by a -1. 2 times -1, 1 times -1, -2 times -1, 5 times -1, and that's what we come up with here. Add a multiple of one row to another row. Well, we're actually going to do this. Row 1 plus -1 times row 2 is going to be a new row 2. Row 1 staying the same. So 1 plus -1 times 1 is 0. -2 plus -1 times -3 is 1. 3 plus -1 times 1 is 2. -4 plus -1 times 7 is. Now in red, we're also going to go ahead and do a little bit of that same 2 times row 1 plus row 3 to give us a new row 3. 2 times 1 plus -2 is 2 times -2 plus -1 is 2 times 3 plus 2 is 2 times -4 plus -5 is. Now this is a little nice in the way that row 1 and row 2 look. Row 1 starts with a 1. Row 2 has a 0 and then a 1. So there are some leading 1s. In row 3, I don't have a leading 1. Also, I don't want to see some number other than 0 that would be underneath this leading 1 showing up here in row 2. So I'm going to want to try to get rid of this -5 and eventually also create a 1 in this particular location if that's possible. So in order to accomplish that, if there was if one of my goals is to kill off the -5, then I'm going to use this green number 1 because the zeros out in front aren't going to screw anything up. I'm going to use this green number 1 right here and I'm going to kill off the -5. In order to do that though, I need to get a 5 times this 1. So what that would mean is I'm going to have to take 5 times my entire row number 2. Add it to row number 3. Hey, and that's going to give me a new row number 3. So 5 times 1 plus -5 is 0. 5 times 2 plus 8 is. 5 times -11 plus -13 is. Now I want that leading 1, so I'm going to want to get, instead of an 18 here, a 1. In order to do that most directly, that would mean that I would multiply by 1 over 18, and that's going to give me a leading 1, and it's going to make that very last entry in my row a not very friendly fraction, but such is life. But what we've come up with now with this sequence of row operations is that we have our row echelon form. Leading 1, leading 1, leading 1. Underneath these leading 1s we have zeros, and above the leading 1s we have other stuff. So we can actually convert this back into a system of equations. The nicest one is the last one, but the first row, we'll do that first. The first row is saying 1x minus 2y plus 3z equals -4. The second row, no x, just 1y plus 2z equals -11. And in the third one, this is why I said it's the nicest one, no x, no y, just 1z is equal to -34 over 9. I've got a third of my answer, or at least what should be a third of my answer. I've got z. And so if I wanted to go through the work here, I could backtrack through and figure out the y using the second equation and the z value, and then backtrack again and figure out the x using the y that I calculate and the z. I don't necessarily want to have to do that. And so if I don't want to have to do that, I can continue working with the matrices and come up with what we call reduced row echelon form. So this should have at least a bit of the same characteristics as row echelon form, but it should be further reduced. And it is, because this is the other requirement here. Other than the requirements that we already stated that got us to row echelon form, above those leading ones, we want to have zeros appearing. So while we have the zeros below the leading ones, and that's wonderful, we would like to get zeros that show up above. So I would want to make this -2 right here in my first row, second column, into a 0. I would like to make the 3 that shows up in my first row, third column, into a 0. And I'd like to make this 2 right here that's in row 2, column 3, into a 0. So I want to accomplish those sorts of things, which means that I would need to have more row operations performed. In order to kill off the -2, I can use row 2. 2 times 1 plus a -2 would cut the mustard, and so that means I would need to take 2 times my entire row 2 plus my entire row 1, and I want to create a new row 1. I want a new row 1 because I want a 0 right there in that spot. So to accomplish that, we would end up getting the purple row that we see here. 2 times 1 plus -2. 2 times 2 plus 3. 2 times -11 plus -4. That's great, and leaves me now with trying to get zeros above the last leading one here, zeros in that third column, second row, third column, first row. So 2 different row operations to accomplish that. -2 times row 3 plus row 2, -7 times row 3 plus row 1. That way I can get a new row 2 and a new row 1 coming out of that. And by doing that work and coming up with those other entries, what I have actually end up accomplishing here with a matrix is that I have converted my system to a matrix, changed the matrix into this special reduced row echelon form, and that actually gives me my solution. First row, x equals. Second row, y equals. Third row, z equals. I've got my solution, or what should be my solution, I should say. I would want to go back and check that for myself and make sure that I am, in fact, good to go. So what we've got going on there, again, a quick little comment back at the top of the screen about that, the solution. Now, if you go through the time and trouble of checking that out, you should find that that is, in fact, the correct solution that we would say. 4 over 9, comma -31 over 9, comma -34 over 9. That's the solution to that earlier system. So we've got these 2 options for using matrices to try to work out what we would have in a system. The solution, hopefully. The first option uses that row echelon form. Let's transform our system into a matrix, transform the matrix into row echelon form. I can then get some information about that system and backtrack. We call it back substitution. We can backtrack through and get the other information that comes out of that. Or we can go ahead and transform our system into a matrix, transform that matrix into the reduced row echelon form, and then that reduced row echelon form literally is going to be giving us what should be our solution. So, to take a look at an example of this and hit you up with those row operations a little bit more, let's look at this particular system here, and you can kind of see how these goals are working out. So, I'm a big fan there of that third row already starting out with a number 1, which means that we're going to go ahead and we are going to do a row 3. I'll tell you what, it might be a little bit easier instead of circling that stuff. Row 3, switcheroo with row 1. So that means row 1 is now going to be 1, 2, negative 3, 12. Row 3 can still, or excuse me, row 2 is still the same. 3, negative 1, 2, negative 1. And then row 1 gets bumped down, so that means negative 2, 1, negative 1, negative 1. I can now use the 1 right here, first row, first column. I can kill off the 3 and I can kill off the negative 2. So I'm going to do 2 different row operations to accomplish that. I am going to do negative 3 times row 1 plus row 2 to give me a new row 2. So let's go ahead and do that. Negative 3 times 1 plus 3 is 0. Negative 3 times 2 plus negative 1 is negative 7. Negative 3 times negative 3 is 9 plus 2 is 11. Negative 3 times 12 is negative 36 minus 1 or plus negative 1 is negative 37. Fill in the rest of my first row because that didn't change. All right, so there's my new row number 2. Let's go ahead and do a new row number 3. 2 times row 1 plus row 3 can give us a new row 3. 2 times 1 plus negative 2 is 0. 2 times 2 is 4, plus 1 is 5. 2 times negative 3 is negative 6, plus negative 1 is negative 7. 2 times 12 is 24, plus negative 1 is 23. Now I'd want to create a 1. Instead of the negative 7, I would want to create a 1. Now I can do that directly, or I can do that a little indirectly. It kind of depends on how frisky I'm feeling about things. So, how frisky do you want to feel? How much or how little do you want to work with fractions in order to accomplish what you need to accomplish? Now, I would like to show you a little bit of fancy pants work. I've got a negative 7 and I've got a 5. If I multiply by a negative 1/7, I get fractions. If I multiply by a 1/5, I get fractions, and I'd rather like to avoid those if possible, so let me try to be a little bit clever. If I add row 2 and row 3 together, I would get a negative 2. Well, that's a little bit better. So if I take that And if I multiply a -2 by a -1/2, that'll get me a +1. So this is a little bit of fancy footwork. I'm going to take row 2 plus row 3. I'm going to times by -1/2. And that's going to get me my new row 2. Row 2. Hand, brain, mouth. New row 2. -7 plus 5 is -2. Times -1/2 is +1. 11 plus -7 is 4. Times -1/2 is a -2. -37 plus 23 is -14. Times -1/2 is a +7. I have managed to do what I needed to do without actually introducing fractions in the mix. Thank goodness. Now, back to the first row there, which again is just being recopied, and the second row now, which I've got locked into place. We would want to create a 1 down, or excuse me, a 0 down underneath of that 1. Down underneath of that 1, I would like to get a 0. So, a 1 versus a 5. I need to take the 1 and transform it into a -5 so that I can add it to this and get a 0. That would mean that I need to do -5 times row 2 plus row 3, row 3 to get a new row 3. -5 times 1 plus 5, 0. -5 times -2 plus -7 is 3. -5 times 7 is -35, plus 23 is -12. And, finally, first row, second row, third row. Well, I want that third row to start out with a 1. It currently starts with a 3, so if I do row 3 times 1/3 to get a new row 3, then I will have a 1 as my leading one. 1/3 times -12 gives me a -4. And so we've got our row echelon form, and we can go through that backtracking, that back substitution. We would say that we've got from the first row x plus 2y plus 3z equals 12. From the second row, y minus 2z equals 7. And from the third row, z equals -4. Because z is equal to -4, y minus 2 times z is 2 times -4 equals 7. That allows me to come up with y equals -1. And then x plus 2 times -1 plus 3 times z is -4 is equal to 12. That means that we've got x, we've got a -2 minus 12, that's a -14 equals 12, so x is equal to, looks like x is equal to 26. Interesting. And so our solution should be shaping up as a 26 comma -1 comma -4. We can go back to our original system and check that. (26) -1 -4. No, something's off there. Must have made a mistake. Where did we go wrong? Let's come back and fix that. All right, try again. y is equal to negative 1. That is true. If y is equal to negative 1, so make sure I didn't lose something along the way. I did lose something along the way. I lost a negative on my first row, third column. Shame, shame, shame on me. Oh my goodness. Did any of y'all catch that as you were watching? Start screaming at the screen? All right. So, try that again, and that would actually mean that x is going to have a, let's see, minus 2 and a plus 12 is a plus 10. That means x should be equal to 2. So let's try that again. 2, negative 1, negative 4. And again, we can come back and check that out. 2, negative 1, negative 4. That seems good. 2, negative 1, negative 4. That seems good. 2, negative 1, negative 4. Hey, that's good. That's working. But this is only one way. This is what we call that Gaussian elimination. We've got reduced row echelon form. Let's actually go back and comment here. Reduced, or sorry, not reduced, but row echelon form. That's row echelon form right there. And we can continue this process by going through and getting the zeros above those leading ones and getting that row echelon form transformed into reduced row echelon form. So let's go ahead and put those entries in there as they are supposed to be, and then continue that conversion. So, taking row 3, 2 times row 3, plus, or excuse me, what I want to go with instead here is negative 2 times row 2. I want to get my 0 in the row 1, column 2 entry. I want to do negative 2 times row 2 plus row 1 for a new row 1. So that'll give me the 0 where I want it. Then I'll have a negative 2 times 4 plus a negative 3. I'll have a negative 2 times 7 is negative 14 plus 12. That's a negative 2. And then my row 2 and my row 3 momentarily stay the same. I would now want to take my row 3 and be able to create my new row 1 and new row 2 because I want to get zeros in my row 1, column 3, row 2, column 3 entries. So if I do negative 1 times row 3 plus row 1, I will get a new row 1. And if I do a negative 2 times row 3 plus row 2, I will get a new row 2. Row 3 stays the same. Negative 1 times 1 plus 1 gives me a 0. Negative 1 times 7, excuse me, negative 1 times 4 plus negative 2. It doesn't help when you talk too fast. Negative 1 times the negative 4 in row 3 plus the negative 2 in row 1 will give me 2. A negative 2 times the negative 4 in row 3 plus, oh, I didn't need the negative 2, I needed positive. Positive 2 times row 3 plus row 2. There we go. That'll work for us now. And get us the 2 times 1 plus negative 2 is 0. 2 times negative 4 plus 7 is negative 1. There we go. Now we've got the reduced row echelon form, which automatically sends us to our solution. From the first row, x is equal to 2. From the second row, y is equal to -1. And from the third row, y is equal to -4. Now, let me make some special notes here, and then I'll come back and show you how you can bang something like this out using the calculator. The comments that we had about special systems, false statements like 0 equals 1, or true statements like 0 equals 0, having an impact on how our systems turn out, we can transform those statements into what would happen in a matrix. So in a matrix, and then just to use a shorter one here for this first example, if we end up doing row transformations and we get something like a bunch of zeros except for the last entry, then that means that what we would have officially is an equation here that's a contradiction. It's a false statement. 0x plus 0y is equal to 1, aka 0 is equal to 1. Well, that's false. That's a contradictory statement. And so this would be a system that has no solution. If we were to go through row transformations and end up with a row of zeros, like we had mentioned before, we could have rows of zeros that show up, then what that means is that we've actually dropped back to having fewer equations than the number of variables. And we said before that usually when that happens, we're probably going to be looking at infinitely many solutions that show up, which means that we would want to try to come up with some sort of format for what those infinitely many solutions would look like. So these are still possibilities, and this is what would happen with the matrices that we're looking at, augmented matrices that we're looking at as we start trying to tinker with things, whether we're trying to get that row echelon form or reduced row echelon form. We would still have things that correspond to those special situations. Now, let me go ahead and very quickly come back to this earlier example that we had. Yeah, here's the system. Just want something to refer back to. So this was the original system, and we said originally that we had, let me go all the way back to the beginning of that example. We said that all the way back at the beginning of that example, let's not use the one that had fractions. I went too far. There we go. Here's our system. This one had the nice solution to it. So here's the matrix. Now I want to show you how you can enter that matrix, and I want to show you how you can tell your calculator to get row echelon form, and reduced row echelon form. So we can actually use that very original matrix right there, starting with the -2, 1, -1, -1. So in our calculator, let's go ahead and clear this. Let's clear that key history so that you can follow along here. We want to do a matrix. So our matrix menu is the little blue one right here. So second matrix. Now this is going to give me a list of matrix names. If I want to tweak that particular matrix, then I'm going to, didn't mean to actually select that matrix. I'm going to edit, there we go, that particular matrix, and I can start by first telling it how big this matrix needs to be. Well, the matrix that we're building is going to have 3 rows and 4 columns, so those are actually set the right way automatically, 3 by 4. Now I'm going to go and type in those matrix entries. So back to the matrix that I have here, I want to type in -2, 1, -1, -1. So, -2, 1, -1. I'm hitting enter each time I move. That takes me across the row, and once I reach the end of the first row, now it drops me to the beginning of the second row. So I'll go look at my matrix. My matrix says 3, -1, 2, -1. 3, -1, 2, -1. My third row says 1, 2, -3, 12. 1, 2, -3, 12. So I hit enter and it keeps me there on that last entry. Now matrix A is all set up. I want to have my calculator do the row echelon form, so I can come back now to my matrix menu, and I want to do math on my matrix. So if I scroll down, maybe I can find REF, row echelon form. So I'm going to select, whoops, forgot to actually get out of there. We need to quit our matrix. Then we'll go back to the matrix math menu and scroll down to the row echelon form option. So row echelon form. Now we want to tell it to use matrix A, so we go back to the matrix menu. There in our names menu, we hit enter for matrix A, and then we hit enter, and it should give us that. Oh my, it's giving us something with a decimal point, 333. Hey, you know what? You can tell it to go ahead and take that and convert it to fractions. Haha. Let's see. Ba-bam! And we can actually go through, we can read that. And I believe it is that if we scroll to the right, it will show us that last row. Now in this particular case, as opposed to ours, this created fractions. So this is not necessarily super useful. If we go ahead and tell it instead, let's go back to our matrix menu, let's go to the math, let's tell it to do reduced row echelon form. Now that should definitely straight up match what we've got. Reduced row echelon form. We want to go back to our matrix menu and tell it matrix A. We want to hit enter, and bingo. 1 0 0 2 0 1 0 negative 1 0 0 1 negative 4. That means x is equal to 2, y is equal to negative 1, z is equal to negative 4, and that directly matches up with the answer that we came up with for that system. So boom. Can we do it by hand? You bet. Do we have to do it by hand? Heck no. We can use the calculator to go ahead and work stuff like that out a little bit more quickly, or if we're forced in some form or fashion to do things by hand, we can at least use the calculator to verify that we're on target there. So at least use the calculator to verify we're on target for the reduced row echelon form, because the row echelon form has so many different possibilities in the way that things can turn out. But the reduced row echelon form, heck, since it gets me my answer directly, I vastly prefer that as an option and would only do the row echelon form if I was absolutely forced to do so.